Welcome to Online Algebra 2. This is section 5-2, polynomials, linear factors, and zeros. So our objective here is to analyze the factored form of a polynomial and to write a polynomial function from its zeros. So finding the zeros of a polynomial function will help you factor the polynomial, graph the function, and solve the related polynomial equation. So in the previous section, we looked at the basics of a polynomial, how you can tell things from the equation like the end behavior, the number of turning points, its name, things like that. Now we're going to start looking at factoring the polynomial and seeing what those different terms actually tell you. Okay? So in chapter 4, we solve quadratic equations in the form x squared plus bx plus c equals 0 by factoring. We wrote it as two linear factors in the form of x minus the first root and x minus the second root equals 0. And we use the zero product property, and we solve that for R1 and R2. And we can solve remember this is the formula for a basic polynomial. We can solve a basic polynomial in the same way, provided it's not too big, okay? So we're going to start with the most basic techniques of how to factor a polynomial. As we get going through the rest of this chapter in later sections, we're going to start to factor more and more complicated expressions. But for now, we're going to use pretty much basic factoring and quadratic techniques to factor my polynomial. So let's start with the first one, okay? So to factor this polynomial, you should always recognize that it has a common factor. And if you're going to factor anything, you should always take out the common factor first. And all of them have an x in common, which leaves me with x squared minus 2x minus 15. Now, I use quadratic techniques, the factors of 15 that subtract and give you negative 2. So that's going to be 3 and 5, and it's going to be x minus 5, x plus 3. Double check with FOIL, right? Make sure your inside and your outside terms actually combine to give you negative 2. And ask yourself, can you go any further? And no, I can't. This is the factor form. It doesn't say solve, right? This is not an equation. It just says what is the factored form of this expression. This is the factored form of my expression, broken into, look at that, 3 linear factors. 1, 2, 3. Let's try it again. Okay, with our got it problem. Again, it has a common factor. It's not always going to be like this, but for now, x squared minus x minus 12, once we factor out the x, and then with my quadratic techniques, factors of 12, the subtracting give you a negative 1, so that's an x minus 4, x plus 3. Okay. So, the following are equivalent statements about a real number being a polynomial. So a lot of people can get some of this terminology the same. And if you have a polynomial equation, remember there's our equation for a polynomial. So if you have a polynomial equation, x minus b is a linear factor if you factor it out to x minus b. Not only is this a factor, but b is a 0, a root, a solution, and the x-intercept of the graph. Okay, so once you have it in factored form, in fact, let's just go back to this one, x minus 5. That means 5 is a root, a 0, a solution, and the x-intercept of the graph, right? This is x minus b. You always, right, solve for x, so it would be x is equal to b. So b is all those things, in the other case 5 is, and as well as negative 3, And don't forget this one, x equals 0. So these are going to be the three roots of this expression. Okay. So what are the zeros of this polynomial? And to start with, it's factored already. So the hard part's already done. So all we need to do now is use the zero product property, set each factor equal to 0. So x is equal to -2, x is equal to 1, and x is equal to 3. Okay. If I want to graph those now, those are also my x-intercepts. Well, that's not enough information to give me a graph. If I multiply all three of the first terms together, my lead term would be x to the third power, which is positive with a odd exponent, which means the left side goes down, the right side goes up. So I know this isn't just like a horizontal line, and it probably has two turning points. So now if I want to graph this, which I do, I'm going to have to make a table. Now, I can use some of the information that I already have here to get other points of interest. So let's plug in, well, I have -2. Let's plug in -3, -1, 0. I already have 1, 2, and 4. Okay, so basically all the points around the thing that I am not sure of. I don't really want to multiply this all out. I don't want to FOIL this all out to get my polynomial in standard form. I could just plug all those different numbers in right now. So that would be, when I plug in -3, that would be a -1 times -4 times -7, which is going to be a -28 off the graph. So it's going to be way below the graph. Okay, so that's good. That means that my graph is doing what I thought. It's going to be going down over here. Okay, let's plug in -1. And when I plug in -1, I get 7. So let me, no, 8, sorry, 8. 8, 5, 6, 7, 8. Then when I plug in 0, I get 6. I've already plugged in 1. When I plug in 2, I get -4. And when I plug in 4, I get something off the graph again, which would be 6 times 3 times 1, so that's 18. That's off the graph. Okay. Now, this looks like the highest point. It might not be exactly the highest point, and this might not be exactly the lowest point, but with our estimation, our graph is good enough. So my graph is going to look like that. A little crooked there. Sorry. But you get the idea. Okay. This graph turns twice. Went down to the left, up to the right. So it did the things that we thought it was going to do that we learned about last section. And all we had to do to get the rest of the information in the graph was plug in points that I didn't have the intercepts to. Let's try it again. So we have x minus 3, and x plus 5. So now my zeros are 0, right? X is equal to 0, 3, and -5. So I'm going to put a dot there. I'm going to put a dot at 0, and I'm going to put a dot at 3. All right, so this one's going to have a lot more points. It's still, my lead term is still x to the third, which means this side goes down, this side goes up. And there's really no shortcut here. You really just have to start plugging in all the numbers in between this. So this might take a few minutes. especially since I haven't graphed it yet. So let's do -4, -3, -2, -1. I have 0, 1, and 2. Okay, so that would be -4 times -7 times 1. Ooh, weird. -28. So it's going to be off the graph. All right, so this graph's not really going to be the right size. So we'll just leave it as an estimation right here. So basically what's going to happen here is that this side is going down, all right, and it's going to sort of turn here and go back down again before coming up back to 0 and then going back down over here. So I didn't quite make the right size for this, but if you plug in all these points, you would sort of be able to get the general shape of the graph. Sorry, this is a positive 28, -28, positive 28. So it'll be way up here, and then it would come back down somewhere up there. So it would be sort of like this, way up here at 28, and then it would hopefully come back down in the next couple. Well, let's see. So that would be -3 times -6 times a positive 2. No, still going up. So that's 36. -2 times -5 times 3, 30. Come back down. -1, -4 times 4. So now we're at 16. And so it would come back down to 0 like this from 16. Plugging in 1, we would get 1, -2. Plugging in 1, 6. So -12. Ugh. This was really a bad picture here. And we got 12 there. And then plugging in 2, it's going to have to come back up here. So 2 times -1 times 7 down to a -14. And it's going to have to come back up to 0 right there. So we got a really weird looking graph here. Kind of something like that. Again, the scale would be, should have been better for this one. But the technique remains the same. This is the important part. Can you get the zeros? The rest is just plugging in everything into the equation. Okay, so the factor theorem describes the relationship between the linear factors of a polynomial and the zeros of a polynomial. So that means that if x minus a is a factor, if and only if a is a zero of the polynomial function. Okay, so that means we can go back and forth. That means if we have factors, we can calculate the zeros, and if we have zeros, we can calculate the factors. So if x is equal to -2, the factor that produces that, when we are solving for roots, we make x equal to the root. When we're solving for factors, we set it equal to 0. So just add the 2 to both sides, and this gives me x plus 2 as a factor. For this one, this gives me x minus 2 as a factor, and for this one, we have x minus 3 as a factor. Okay. Well, there's my polynomial, or actually, let's use function notation. There's my polynomial. However, it's not in standard form. Okay. So what we have to do to make it standard form is multiply everything together. Now, I would suggest multiplying these two together because we have two conjugates. And when we multiply two conjugates together, the middle terms cancel out, and that just turns into x squared minus 4. Right? And then when we FOIL these together, we get x to the third with my first terms, my outside minus 3x squared, inside minus 4x, and last is plus 12. Okay, so not much to that, right? We have 3 zeros. we're going to have a third degree function. We just have to multiply all the factors together. And that gives me my cubic polynomial. Look, cubic polynomial of 4 terms, even though that doesn't look like a 3. Now, what happens with a quartic polynomial? Let's look at this, and we're going to look at the graph of both of these in a second. Notice that these two zeros happen twice, and also notice that these three are the same: -2, 2, and 3, the same as the first problem. So all we're doing is tacking one more on there. So my function would be x minus 2 times x plus, let's write it the way we did up there, x plus 2 times x minus 2 times x minus 3, and then this one more x plus 2. Now I already know when I multiply these three together, I get the answer that I just got in the last problem, x to the third minus 3x squared minus 4x plus 12, and I can just take that and distribute it to x plus 2 to get my answer. You could have done this all over again, right? Multiply these two together, then the answer to that, then the answer to this, all right? But we already have those three multiplied together, okay? Distribute, we're going to distribute this to both of those. So that gives me x to the fourth plus 2x to the third, these two. So that's minus 3x to the third minus 6x squared. The 4x to both of those, minus 4x squared, and a minus 8x. And the last is plus 12x plus 24. Okay. Combine the like terms. There's no other x to the fourth. These two are x to the third, so I get a minus 1. These two are both x squared, so I get a minus 10. These two are both x's, so I get a plus 4x plus 24. And there is my quartic polynomial of 1, 2, 3, 4, 5. Quartic polynomial of 5 terms. Okay. Now, the last question here says graph both functions. Okay, and before we do that, let's think about what we expect. We expect this graph to have 3 zeros, 3 intercepts, probably 2 turning points, the left side going down, the right side going up. Okay, this graph, we expect to have 4 zeros, maybe 4 intercepts, but it's weird that these two happen twice. So what's going on there? 3 turning points and both sides going up. Let's see what they look like. Okay. So here's my graph. This one, the cubic, looks just like I expect. The left side going down, the right side going up, 2 turning points like this, 3 intercepts, the 3 numbers that I got. But look what happens on the quartic one. Both ends go up, yeah. Okay, so I expected that. It has 3 turning points, but look at what happens at -2. It's an intercept, but the graph touches the x-axis and bounces the other way. It does not go through the axis like all of these intercepts, okay, or like these two. Okay, not only is it an intercept, it's also a turning point. Okay, so that happens when we have a multiple 0. Okay, so we can write the polynomial function in problem 3 in factored form in these two. We just got that, right? We can write this one as x plus 2 squared. And because it repeats its linear factor, we have something called a multiple 0. If we have a multiple 0, if a factor appears twice, The way we say it is that -2 is a 0 with a multiplicity of 2. If it happened 3 times, we would say -2 is a 0 with a multiplicity of 3, 4, 5, 6, whatever. Okay? So the word multiplicity implies that the 0 happens more than once. And that definitely affects the graph, like we saw. So if A is a 0 of some multiplicity n in the polynomial function, then the behavior of the graph at the intersect, if the 0 happens once, it will go straight through the x-axis, just like the cubic function did. If it happens twice, it's going to look like a quadratic. It's going to hit the x-axis and bounce. If it happens 3 times, it's going to flatten out and go through the x-axis, kind of like that, kind of like a cubic. Then take it from here. 4 times would look like a quartic, 5 times would look like a quintic, but it is very hard without a graphing calculator to distinguish between a quadratic and a quartic and a 6-degree polynomial. So we're going to stick with 1, 2, and 3, all right, because those are very, very different. Here's kind of what they're going to look like. Let's factor this first. Okay, so here's my polynomial. Let's factor it and find the multiplicities. Notice it has a common factor. So f of x, factor out the common factor, and we get x squared minus 2x minus 8. So x squared, and then the factors of 8 that subtracted 2, x minus 4, x plus 2, okay? Which means that my zeros are, let's save this one, -4, positive 4, -2, and this one, which happens twice. So it is 0 multiplicity of 2. And that's how we write that with a sort of shorthand. So we put the root, we put MULT, period, multiplicity, and then we put the multiplicity, 2. So now, based on what we just talked about, the graph will go through the x-axis at those 2 points, but here it's not going to go straight through. It's going to touch the x-axis and bounce the other direction. And here is my graph. So you can see intercept, intercept at -2 and 4. But at 0, it bounces the other way and it looks like a quadratic. Upside down, but quadratic. At -2 and 4, the graph will go straight through. Okay. So let's do the got it problem here. Again, let's just factor it and analyze it. So f of x, when I factor this, I can factor out an x. That gives me, and let's factor this, x squared minus 4x plus 4. And that factors into factors of 4 that add up to -4, x minus 2, x minus 2. And a better way to write this would be x minus 2 squared. So that means that x is equal to 0, this one, and 2 with a multiplicity of 2. Okay, so that means that this graph crosses the x-axis at 0, touches the x-axis and bounces the other way. It could be up, could be down, I'm not sure. At 2, I mean, we could logical it out, or we could draw the picture, but either way is going to touch the x-axis and then go the other direction. So if the graph of a polynomial function has several turning points, the function can have a relative maximum or a relative minimum. The minimum is the point where the graph changes from going down to going up, and the maximum is the place where it's going up and now it starts going down. And we say relative min or max because this is not the minimum of the function. This function goes down to -infinity. This is not the maximum. It goes up to +infinity. Okay, so we're just saying that these are the places where they change direction. And without calculus, without finding the slope of the curve at those points and figuring out what the slope is equal to 0, we're not going to be able to calculate them, but we can use a graphing calculator. So let's see if I can't factor this a little bit, and then just for practice, and see what I would expect from this. So if I were to factor this, they all have a x in common, x squared plus 3x minus 24. The factors of 24, that subtract to 3. No, not going to factor easily. So we would know that we have a 0 here. No, we're going to have, we could solve this, right? We could use the quadratic formula, but I don't really want to. So when we look at this and we graph it, okay, we do have two nice points that are mins and maxes. Again, that's not something we'll be able to calculate here. And you can see that my intercepts there and there are not particularly nice numbers. They're real, so we could easily calculate them with the quadratic formula, but they're not going to be nice numbers for the graph, for the points of graphing this. Okay, but this is the, what's the way I say this right here? The relative maximum occurs at -4, and the maximum is 80. So the way you say it kind of tells the reader whether or not you're looking for the x coordinate or the y coordinate. The relative minimum occurs at 2, and the minimum is -28. That is the lowest thing on the function. Okay. Let's finish with a word problem. 2 word problems. So the design of a digital box camera maximizes the volume while keeping the sum of dimensions at 6 inches. Length must be 1.5 times the height. What should each dimension be? Okay, so let's work through this. So x is going to be the height. The length is going to be 1.5 times the height, and the width is going to be, well, the sum of the dimensions has to be 6 inches, so the width is going to be 6 minus the other 2. So that's the height and the length. Okay, and if I distribute that, I get 6 minus x minus 1.5x. So that's 6 minus 2.5x. And that is the width. Okay? So we want to, the goal of this problem is to maximize the volume. So in order to maximize the volume, and the reason why I did this was to make them all in terms of x. Now we have length, width, and height all in terms of x. So the volume is going to be x times 1.5x times 6 minus 2.5x. And now I have a good formula for volume. Right? Distribute this all together. The first two just give me 1.5x squared. And when I distribute to everything, we get negative 3.75x to the third. That's these two. 1.5 times negative 2.5 and plus 9x squared. Now, that is not an easy polynomial to find the min or the max of. So your real strategy here would be to graph it. And when I do graph it, now I can see, now I can see the maximum, right? That's the maximum volume. So if x, which was the height, so if the height was 1.6, my maximum volume is that. It's not one of these numbers over here because the height can't be negative. And then once we get too big, the graph doesn't come back up. So we can eliminate all these negative answers right here because that doesn't make sense. And we're just looking at the usable domain, which is any of those numbers right there. And now the volume is at its maximum. One more problem. And this problem's a little bit better. That other one's a little silly. This one's a little bit better. So a metal worker wants to make an open box from a sheet of metal by cutting equal squares from each of the corners. So you're going to chop this out right here, okay? And then what you're going to do is you're going to fold up the box. You're going to fold it up right along this line, once you chop these corners off to make a box. So write the expression for the length, the width, and the height. So if I wanted to, I would now be able to write the formula for this as long as I knew the length. Well, the length of the whole sheet was 16, so this would be 16 minus the 2 pieces that I cut off. This piece would be 12 minus the 2 pieces that I cut off, and the height is just x. So the volume of the box would be x times 16 minus 2x times 12 minus 2x. Write a function for the volume. Okay, so again, I'm going to have to distribute this. So we get x times 192 minus 32x minus 24x. I'm just distributing this, foiling it together, 4x squared. I'm going to rearrange these and distribute the x to give me 4x to the third, this one times this one. These two combine together to give me a minus 56x squared once I multiply the x in there, and then plus 192x. Again, not an easy graph to try to draw. So my suggestion would be a graphing calculator, something like Desmos, that you can graph the function and give it a shot. Graph that and then see where the maximum volume of the box would be. Again, just remember that either one of these can't be negative, so that means this is your limiting factor right there. X has to be somewhere in between, and we don't want it to be 0 and 6, not including 6. So somewhere in between there is my domain of my usable answers. Because if x is bigger than 6, now this side is, now we're chopping 6 inches off of here and 6 inches off of there. We don't have any sheet left to make a box. Okay, so covered a lot in this section. Hopefully you guys followed it all. The zeros of these functions, right? 0 and 6, -4, +5, -12, +9, +7. And again, if you're going to write that polynomial, that would be x minus 1 times x plus 1 backwards, and x, not a 0, right? The single x is what gave you your 0 as an answer. Okay. Now this is a good one. Write a polynomial in function h in standard form that has 3 and -5 as zeros of multiplicity 2. So that just means that h of x would be equal to x minus 3 multiplicity 2, x plus 5 multiplicity 2, and then you'd have to FOIL those all together. Okay. And that was 5-2, polynomials, linear functions, and zeros.